Okay, welcome to the video for exercise 4 on page 78 of the workbook here. And this is another problem where we're trying to find a maximum or a minimum value of a function in an applied situation. And this problem is about a rectangular box. Okay, if we read the problem together, they're telling us in this case that we have 1200 square centimeters of material available, okay, to make a box that's missing its top panel, and we want to know what is the largest possible volume of the box. Okay, so given the material we have, we can build this box in a lot of different ways. We can make it tall and skinny or short and fat, and they're just asking, how would we want to choose the x and the y that you see the dimensions so that we get the maximum possible volume? Okay, well, let's try setting this problem up the way that we've been doing by starting out and asking ourselves, what is it that we know in the problem? Okay, well, the biggest piece of information they give us is the amount of material that's available, 1200 square centimeters. That's about the area of the box, so we might start by asking ourselves, how many pieces are there to the box? Okay, well, they tell us that it's missing its top panel. That's important to remember. So if you think about it, we've got a bottom of the box, that's one side, and then we've got the four outsides, the back, the front, the right, and the left. So that's four more sides to the box. All right, so what we basically need to do is just to add up the area of all five of those pieces. So let's start with the bottom. What is the area of the bottom of our box? Well, that has the shape of a square, so it should just be x times x. Okay, so there's the area of the first piece of our box. And then we've got the four panels around the outside. Let's maybe highlight the right-hand panel. What would the area of that be? Okay, well, that's a rectangle that has a width of x and a height of y, so its area should be x times y. And if you think about it, there are three other pieces that have exactly the same size. Okay, the back, for instance, that also has a width of x and a height of y. And so we've got four pieces that have area xy. And so 4xy would give us the area of the front, the back, the left, and the right. Okay, so adding those two things up should give us the total area that we have available, which they tell us is 1200 in this case. So that's what we know. Okay, what are we being asked to find in the problem? Okay, well, they'd like us to find the largest possible volume. So we need, well, let's just write that in words first. The maximum, I'm sorry. What we want is the maximum volume. Okay, let's give it a name and just call it V. All right, so if we want to maximize the volume, we need a formula for the volume. So here we have to think back to geometry a minute. How do we find the volume of a rectangular box? Okay, let's first maybe get rid of some of the markings that we put on this. Okay, well, you might remember this from geometry, or it might be something that you need to look up. Okay, a lot of times in a problem like this, I would tell you what the formula is. To get the volume of a rectangular prism, you can just take length times width times height. Just multiply all three of those dimensions together. Okay, so we can kind of see how our box is labeled. That means we're going to take x times y. If you multiply those three things together, you're going to get x squared times y. There's our formula for the volume of the box. Okay, and since we need to maximize that volume, we're going to need to find critical points, which means we need to take a derivative. But we run into the same problem that we keep running into. We've got two variables, x and y. We can't take the derivative until we reduce that down to one variable. Okay, so here's where we're going to go back to our given piece of information. Okay, the x squared plus 4xy equals 1200, and we need to take that and solve for one of the variables. So which variable do you think would be easiest to get by itself? Okay, I would probably choose y because it's raised to the first power, so that's the variable that I'm going to try to solve for. Okay, let's see if we can sneak that in over here. So if we maybe subtract x squared from both sides of that equation to get us started, okay, we're going to get that, and then we can divide both sides by 4x. Okay, to get a formula for y. Okay, now before we continue, I don't know if you tried this problem on your own yet, but if you haven't, this is just a recommendation. I'd encourage you to maybe pause the video at this point and see if you can finish the problem, or at least take it a few more steps on your own. I think that would be very useful to give that a try. Okay, and after you do that, you can watch the rest of the video and compare what I did to what you've done. Okay, so that said, let's continue with this. So, we figured out what y was. Okay, so we can go ahead and substitute that in for the y over here in our formula for the volume. Okay, and we need to take the derivative of that function to find our critical points, but this would be a pretty ugly derivative to take. Okay, we've got a product and a quotient, and so it's going to be to our advantage to simplify if we can. Okay, and so just to do that, notice we can do a little cancellation with the x's if we remember that x squared is really like a little fraction in its own right, x squared over 1. Okay, thinking about it that way, it allows us to cancel those x's there, and to rewrite our function like this: x times 1200 minus x squared over 4. Okay, and then let's take the x and distribute it through the numerator. That's going to turn this into 1200x minus x cubed over 4. Okay, and to make it even a little easier to take the derivative, let's rewrite that fraction as the product of 1/4 times 1200x minus x cubed. Okay, that's the same volume formula that we started with, just written in a form that's easier to take the derivative of. Okay, and so we're ready to find our critical points here. So we're going to take the derivative of v, and I'm going to use the formula here because that was the simplest one, the one that was easiest to take the derivative of. So the 1/4 is a constant that we can pull out. We're going to multiply it by the derivative of the part inside. So the derivative of 1200x is just 1200, and the derivative of x cubed is 3x squared. Okay, we'll take that and set it equal to 0. And so we need to solve that equation. And so we can start by maybe multiplying both sides by 4 to get rid of that fraction. Okay, those 4's are going to cancel. And that's going to leave us with 1200 minus 3x squared equals 0. And we need to solve that equation for x, so let's add 3x squared to both sides. We can divide through by 3. Okay, let's see, 1200 over 3, I think that's a nice number. That's going to be 400. All right, and then solving for x, we can just take the square root of both sides. Normally in this situation, we'd take the plus or minus square root, but we know that x is a positive number because it represents a length, so we really just need the positive square root. Okay, and the square root of 400 ends up being 20. What would the units on that 20 be? Okay, well, x represents a length, and in this problem, length was in centimeters, so that should really be a length in centimeters. Okay, now, looking back at the top of the problem, what they wanted was the maximum volume of the box. If we've done everything right, since this is our only critical point, this should really be where the maximum volume occurs. Technically, it might be nice, okay, to do a little sign chart and confirm that we have a maximum here. I'm going to skip over that step, though, since we've just got one critical point here, and go ahead and see if we can answer the question here. Okay, so maximum volume. So we want to know, what is the volume of the box at x equals 20? Okay, well, what was the formula that we came up with for volume? If you look back up at our work, that was this formula right here that we underlined. Okay, so we're just going to take 20 and substitute that in for x. That should give us the maximum volume. Okay, and you can double check my calculations here. Okay, maybe substitute that into your calculator, and what you're going to come up with is 4,000. And what would the units on that answer be? Okay, well, if length is measured in centimeters, then volume should be measured in cubic centimeters, and so that should be our answer. Okay, and it looks like we have finished